Alright guys, today we're going to talk about vector valued functions. Although we kind of have already talked about them. Why? Well, because remember when we talked about parametric curves, we said that say we had x to t equals some function. Let's say for example 4 cosine of t, and then y of t we said was 3 sine of t, let's say. And then we had z of t equals to t. But if we now think about putting this together as a vector, so we can say that the function r, as a function of t, is going to be equal to the vector that has coordinate x of t, y of t, and z of t. All right, so that gives us a function that is taking values in a vectors. Therefore, it's called a vector valued function. And now we should probably call this that. So it's a vector. And we can also write it in terms of coordinates as x of t times the standard vector I, which is 1, 0, 0, plus y of t times j. That right there gives you a two-dimensional vector. But if you had 3 dimensions, then you have z of t times k. Right, so that's what a vector value function is. Just going to be a function that takes values. If you want to write it mathematically, it would be a function that goes from R, so grabbing values in R, and goes into R, either 2 or 3. Let's say 3 right now, and so meaning that grabs vectors, or sorry, variables in the reals, namely t, and gives you a vector out. So that's what a vector value function is. All right, so the first question you want to do is what happens with the limit. So how do you define the limit? So we will go ahead and define it. I'm going to erase because, you know, my issue with space. I'm going to erase it and I'm going to come back and we're going to define a limit. All right, so we'll talk about a limit. So what kind of objects do you want the limit as t goes to a of r, which is a vector of t? What kind of objects firstly do you expect to have? Well, you would expect that that would be a vector. So we'll say that that is a vector. Let's call it L for limit, and we'll say that is a vector. If and only if, well, I would have to do a epsilon delta definition, but I'm going to simplify and just say that using the norm topology. So I'm going to say that if the magnitude of R minus L goes to, in terms of the limit of as t goes to a, this goes to 0. And now, that of course would be our definition, but how do we actually compute them? So this is a theorem that you would end up having to show that with this definition, then the limit would be the following. So in this case, I'm just going to write L will be equal to the limit. Not going to have room there. Limit as t goes to a of x t times I plus, let's see, maybe I can fit the limit here. Limit as t goes to a of the y, I should have said y t, and am I out of room? Probably j, and then the limit as t goes to a of z t k. Meaning, all you have to do to take your limits is take the limits coordinate wise. So that is that. So it's not that difficult. So whenever you want to take limits for a vector value function, what you're going to do is you're going to compute the limit point wise. So for example, you wanted to do the limit as t goes to pi over 2, I don't know, something. In this case, not going to evaluate it, but say that your function is given by cosine of t, sine of t, and then, I don't know, just t, another helix. Not much imagination, I suppose. Well, you take the limit of each one of them. In this case, the limit would be direct evaluation, but the point is just that not to show you how to do limits because you've done so many, but how the vector value functions limits, or limits for vector value functions work. So if you take the limit at this one, limit as t goes to pi over 2 of cosine is going to be 0, and then sine of t as t goes to pi over 2 is going to be going to 1, and this is just going to be going to pi over 2. Of course, you can get as creative as you want. You may need L'Hopital's rules or whatever, but you're going to be doing term by term. So that's the whole point. I don't want to dwell too long in this. I do want to start looking at derivatives, and then we're going to do some examples with that. All right, so let's take a look at the derivative. So let's say that r is going to be given again in terms of x, y, and then z. Doesn't have to be three-dimensional. I'm going to write it like that because that's the most general we'll do. But we can do in general. We can do it for 2 dimensions. And now we want to look at what happens with our derivative. So then the derivative would be given by the limit as h goes to 0 of r of t plus h minus r of t all over h. I think that marker is kind of giving up the ghost. Let me change it. I'm gonna get a new one. It should look better. All right, so let's take a look at what that would mean. Well, this, if we write it over here, would be, oh yeah, the limit as t as h goes to 0 of, and now we have to evaluate this right here. Now, what this vector will give me is going to give me the vector x at t plus h, y at t plus h, and then z at t plus h, minus, I'm going to write it down below even though it's a big quotient, x at t, y at t, and z at t, all of it over h. Kind of funny to write it like that, but just space. And now if you think about how we operate vectors, this is just going to be the limit as h goes to 0, and we're going to evaluate them coordinate wise. So this 1 over h would go inside, and you would end up with x. Oh, I know why the x is I'm having trouble with it. T plus h minus x of t, all over h. And then the next coordinate would be the same with y. So y t plus h minus y of t. I don't know if I fit that one there over h. And then the last coordinate would be z t plus h minus z t all over h. And that would be nothing but whenever you move the derivatives, the limits in and out, because remember that's what we said that we could do with the limit, that would take the limit coordinate wise. And that's the theorem that we had to show. We really, based on the definition, we don't know a priori that that's what would happen, but that is what happens. So once I can move the limit in, I get nothing but x prime, y prime, and then z prime. So meaning that the derivatives, you also can take coordinate by coordinate. So let's go ahead and solve an example where we draw a graph of a function, we find a derivative, and find a tangent line to that curve. So let's go ahead and look at the curves, a specific curve, and let's solve an example. So I'll erase and I'll be right back. All right, so let's start with one example where our function, we kind of wrote it before, that's the one I have in mind for today, is a helix. So we're going to try to do everything in one example. So we're going to start with 4 cosine of t, 3 sine of t, and then t. So the first question for us is, well, we should graph it. So we graph it, and then let's find the tangent line to that curve, whatever we obtain, at pi over 4. So we're also going to need to take the derivative at pi over 4. You can see I'm struggling with these markers. I should already have given them to my daughter to color. Oh well. Anyways, So let's go ahead and compute this. So first of all, I'm going to draw the graph. So this is 3 dimensions, x, y, z. So I'm going to have to do a 3-dimensional plot. And so how do you do it? Well, you have to do it as we've done parametric curves. So you have to make a table. So let's go ahead and make a little table. Since I'm going to go at pi over 4, I'm going to try to go from 0 to 2 pi for my table and see how we do. So I'm not going to be extremely detailed because I know what the shape of the graph will be. But if you don't know the shape of the graph, you'll have to plot a lot of points. So I'm going to have here, for example, t. And I'm going to start with my XYZ coordinates. So that's why I made that long line and I didn't remember what I was doing. So here's my X, my Y, and my Z coordinates. And just like we did before, parametric. So start at 0. So cosine at 0 is 1. So this becomes a 4. Sine at 0 is 0. So that's 0. And t at 0 is 0. So that gives me a point that I can go ahead and plot. So grab 1, 2, 3, 4. Let's say that 3 and 2 and 3 are too close, but let's start at 0. 4, 0, 0 is going to be right there. So I'm going to need to go all the way to 3 for this one. I know that. And for z, I'm going to go all the way to 2 pi. So it's probably better to do it in multiples of pi over 2. Pi over 2 is about, or pi over 4, which is close to 1, let's say. So pi over 4, let's say there. Pi over 2. 3 pi over 4. Pi, let's say here. And then I guess I'm not going to go all the way to 2 pi. But that'll give us enough of an idea. So 5 pi over 2 and, pi is over 4. So it's going to be 5 pi over 4 and then 6 pi over 4, which is 3 pi over 2. Anyway, so let's go ahead and do multiples of pi over 4 here, which is what I drew there. So pi over 4, pi over 2, 3 pi over 4, pi, and then let's go to 5 pi over 4. I think that's where I'm going to end because I don't even know if that one fit in the graph. But anyways, I'm going to write the values. So when t is pi over 4, x is going to be 4 times the cosine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2. So this is going to be 2 root of 2. This one, when we evaluate, sine of pi over 4 is square root of 2 over 2, which is 3 root of 2 over 2 here. And then here I get pi over 4. So let's try to plot that point. Now, the root of 2 is 1.4 roughly. So 2 times that is going to be about 2.8. So it's going to be somewhere 1, 2. 2.8, let's say, is around here. And I'm going to go 3 square root of 2 over 2, which is going to be, let's say, 3 over 2 is 1.5, and times 1.4. Ooh, that's going to be 1, and so don't laugh, 2.1 roughly, something like that. So I'm going to go this way and this way. So I'm going to be somewhere here. Drawn to scale, not. And I'm going to be going up pi over 4, which is what I grabbed this quantity to be. So I'm going to be somewhere out here. All right, so that's my second point. Now my third point is going to be pi over 2. I'm going to plug it in here. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so that gives me a 3. And this is going to be pi over 2. Oops, I want to write 4. Pi over 2. That's what it is. All right, so now I'm going to go to 0 in the x and 3 in the y. So I'm going to be here. And I'm going to be going up by 2 of this. So 1 and 2 somewhere here. So you see at the moment, I have this graph is going in this direction. And then it's going to turn around. Whenever you have sines and cosines, you know there's going to be something like an ellipse or a circle going on. The t is just moving it up. So there'll be a helix going on. So 3 pi over 4, the cosine of 3 pi over 4 is going to be negative now. So it's going to be negative square root of 2 over 2. And that's going to give me negative 2 root of 2. And then at the pi over 4, for the sign, that's still positive. So I'm going to still have this 3 root of 2 over 2. And then here I'm going to have the 3 pi over 4. So where's that point? Well, it's going to be more or less here, but reflected on the other side for the x. So I guess I got to go a little bit further. And I'm going to go roughly 1, 2, 3. So around 2.8. That's what we agreed it was. And if it was not, well, by symmetry, we'll keep going there. And this one is going to be the same value of y. So I'm going to be here. And then I'm going to be going up by 3 of these quantities. 1, 2. So 1, 2, 3. So somewhere up here. That's going to be my point. So it's kind of going behind now. And now I'm going to do one more only. So pi, at pi, the cosine is -1. So -4 now. And then this is going to be 0. And this is going to be a pi. So I'm going to be going back to -4. So further back even. So I'm going all the way here. In y, I am at 0, but then I'm going to be going 4 quantities up. So roughly there, 1, 2, 3, 4. So all the way back here. So it's going to be it's going to be turning around. It's going to be going around and around, up and up. That's the best I can draw. So please don't laugh. That's what I do. I'm going to plot it in Desmos. In fact, I already did. And I'm going to embed the graph in here once we do the tangent line. So I'm going to embed the graph with the tangent line. It's going to look beautiful. And by the way, Desmos/3D, I'm not affiliated to anything. I just find that the product is fantastic. It's free. And yeah, use it. Anyways, so let me go ahead. Now we need the tangent line. So technically what I want to do is find this line that goes here and what would be the parametric form of that tangent line. So again, tangent line, you still want to do your derivative, but the derivative gives you a vector. What in the world does that vector mean? Well, the vector, by the way, this graph has a this plot has a direction. It's a parametric curve or a vector value function. So it's going in this direction as you draw it. And that will then give you, following this direction, the tangent vector you obtain by taking the derivative will be the vector that is tangent to this line and going in this direction. And of course, that means that you can find unit tangent vectors. But I'm not going to do unit tangent vectors at the moment. I think I'm going to do a full lecture on that. I'm going to just find the equation for the tangent line in parametric form. All right, so I'm going to erase here so I can take my derivative and then I'm going to finish. So I can probably fit everything within the same screen and having the graph there. I think that's what's going to be this video. That's going to wrap up the whole video. So let me go ahead and erase. I'll be right back. All right, so now we're going to take that derivative that we advertised from the beginning. The derivative of the cosine is negative sine. So -4 sine. Derivative of the sine is the cosine. And the derivative of t is 1. All of this has to be evaluated at pi over 4. So I'm going to write here t equals pi over 4. Barely fit it. I had to move it below, but it worked out. So we just have to evaluate, and that's going to give us a vector. Again, the derivative is a vector. So let's take a look at that. We evaluate pi over 4, which is square root of 2 over 2. So that's going to be -2 root of 2. And then the cosine is going to give me square root of 2 over 2. So I'm going to write as 3/2 of root of 2. And then, well, I don't have to evaluate anything because the derivative was 1 already. So this vector would be the vector that I obtain here. Now I have to, with a vector that directs the line, so a director vector for the line, I need to then determine or write the parametric equations for that line. So how do I do it? Well, I know the director vector, which is going to be playing the role of a slope. I need a point. So I got to evaluate this function. And by the way, I forgot my vectors. I got to evaluate it at the time that I was given. So pi over 4. And that's going to give me the point. And then I'm going to show you how you put together put that together in a parametric form for the equation. So let's go ahead and plug it in into the original function. So it's going to be, again, I chose a point where the sine and the cosine gives me the same. It's cheating. Anyways, so for cosine of pi over 4, cosine of pi over 4 is square root of 2 over 2. So I get 2 root of 2. Now for this one, I get, again, 3/2 of root of 2. And then I have here, when I evaluate the times equals pi over 4, I get the point is pi over 4. So how do you translate that into your parametric equations for the line? Well, you start with the x, of course. You grab your vector, your coordinate of the vector. Maybe some colors will help. So I'm going to grab the x coordinate of the vector. I'm going to put it here. So negative root of 2, or 2 root of 2. And I'm going to multiply that times t. That is to make all the scalar multiples of my vector. And then I'm going to add the x coordinate of my point. So 2 root of 2. Well, funky color. I was not expecting to write that. I was going to write in green or yellow or whatever the color it may be. Now, for the y, you do the same thing, right? So you grab your y, which is going to be 3/2 of the root of 2. Oh, that's horrible. Okay, well, the parentheses save it, but that's just not the way you should write things. And then plus that same thing. So I'm going to write it correctly this time. So 3/2 root of 2. So it's very clear who's dividing, who's multiplying. Otherwise, you end up with those memes of, oh, so what is the result of that, whatever operation? And z, I'm not sure I can fit it. My monitor is blocked, sorry. But I'm going to write it. Hopefully, it does fit. And that's going to be your derivative is 1. So you're just going to have t times 1 plus pi over 4. And as I said, I plotted this on Desmo, so I'm gonna put it in the screen. Hopefully you can see it. So that's how you will find your tangent lines to a curve in whenever it's a vector value function, and you're gonna find your lines in parametric form. Of course, you could transform this also in a vector value function because there's that duality we spoke earlier, that they're very, very similar to one another. All right, I'm going to stop right here. I hope that you enjoyed it, and I'll see you in the next one. Thank you for watching.